This slide is on the topic of the population analysis and atomic charges. Population analysis and atomic charges. The first subtopic is the population analysis as the general description. The second is the molecular analysis. This is the method based on the LCAOs as the default method. The natural bond orbital analysis is the popular method to compute the partial charges of the atoms in molecules charge. The last topic is the example to evaluate partial charges using the DFT calculation at D3LYP /631G, the level of theory. Population analysis. The question is, what is the population analysis for? The answer is, the population analysis is the study of charge distribution within molecules. The intention is to accurately model partial charge magnitude and location within a molecule. This can be thought of as a rigorous version of assigning partial charges on the atoms, like chemists often do in Lewis dot structures. For example, the structure of the hydrogen fluoride. Hydrogen can be shown as the positive partial charge, and for the fluoride can be negative partial charge. Partial atomic charges are not observable characteristics of molecules, and therefore the entire idea of modeling electron population is not unique. Molecular analysis. The molecular population analysis is by default always performed in Gaussian. This population was found by Robert S. Mulliken, the American physicist. It is based on the linear combination of atomic orbitals, or LCAOs, and therefore the wave function of the molecule. The electrons are partitioned to the atoms based on the nature of the atomic orbitals contribution to the molecular wave function. For the example of the molecular population analysis obtained from the calculation of the DFT method D3LP using the 6,311 plus G, the basis set of the ammonia molecule. The result, the molecular charge for the nitrogen is equal to minus 1.048 electron. And for the hydrogen, 3 hydrogen have the same number of the molecular charges is equal to 0.349 electron. The charge density rho I as a function of position for one electron in the point R computed from the orbital phi I as function of R can be computed from the equation 5.1. Charge density equal to the phi I star multiplied with phi I. In the calculation, such as RHF or resistive Hardy-Fock, there are 2 electrons in each orbital. Therefore, the charge density can be double value of the 1 electron, as shown in equation 5.2. The total wave function accelerated determinant with m orbitals of the quadrature molecule can be obtained from the equation 5.3. The charge density is equal to 2 of the summation I orbital to m orbital of phi star multiply phi I. Insert orbitals or the bases into the equation 5.3. Therefore, we can get the value on the next slide. To insert the bases or orbital this equation into the equation 5.3. Therefore, the equation 5.4 is obtained. The value surrounded by pink dot line. If we define P of A, B, mu nu is equal to the summation I equal to 1 to m orbitals of 2 C A I mu times C B I nu. We can get the equation 5.6. The equation 5.5 is called the density matrix. The total number of electrons n is obtained from integration over all space, as shown in equation 5.7. This equation is derived from the equation 5.6 by insert the sigma rho into the integration over all space. The product is the summation from A mu summation from B nu of the density metric D from the equation 5.5 multiply with the integration of chi mu AR times chi nu B R dV. As we know that the S mu nu AB is the overlap interval or S matrix. Therefore, we can short the equation 5.7 as equation 5.9. N equal to D matrix times S matrix. For the definition, the net population on atom A or Na can be computed using the equation 5.10. The overlap population between different atoms A and B is mean A not equal B can be written as shown in equation 5.11. O matrix O subscript AB is equal to summation mu A summation nu B multiply with the density matrix multiply with the overlap matrix. The overlap population gives a measure of the bond strength between atoms A and B. The gauge population on atom A can be written as PA, which is equal to Na plus summation B of 1/2 of overlap populations as shown in equation 5.12. Note that summation A on PA is equal N. The charge on atom A can be therefore QA equal to ZA minus PA. Furthermore, the gauge population can be partitioned into different types of populations depending on the type of atomic basis functions, such as S population, P population, D population, and so on, where S, P, and D are S, P, and D orbitals respectively. These partitioned populations give information on the atomic space, in particular the populations for transition metals. For the open shell calculations, spin populations can be obtained from the equation 5.14. Spin population SA is equal to PA, gauge population of the alpha electron, minus gauge population of beta electron. The spin population gives information on oxidation state, particularly of the transition metals. Note that population analysis is somewhat arbitrary and it depends heavily on the basis set. More Sophisticated procedures are generally not more correct, but may serve a particular purpose better. Natural-born orbital analysis. Based on the theory of the natural orbitals by Lodin or Lodin population analysis, there are two parts of the methods. The one is the NPA method for natural population analysis to identify the population numbers. The second method is the NBO for analysis of the bond order based on the electron population obtained by the NPA method. The NBO charges compare with the molecular charges of N nitrogen hydrogen atoms of ammonia molecule. They are slightly different. The advantages of the NBO are as following. The first, the small dependence of the basis set. The second is better reproducibility for different molecules. The third advantage is the orientation itself as the formalism for Lewis formulas. The molecular and NBO charges of the nitrothiol isomers derived from the DFT BCLYP/C1GD method. The molecular and NBO charges of the isomer of nitrothiol are shown in the tables below. There are 5 isomers such as C, C', T', Z, and T isomer. There are 4 atoms in each isomer: sulfur, nitrogen, oxygen, and hydrogen atoms. The Z isomer, molecular and NBO charges are quite similar, but for other isomers, they are quite different. As a charge distribution analysis, as we know that the molecular charges is the default obtained from the LCAO-MO calculation. The molecular charges N is equal to the density matrix multiply overlap matrix S. Lodin charges derived from the molecular charges as N equal to S power minus 1 times D times S power minus 1. NBO is the natural-born orbital method. The AM1 is the atom in molecules method. ESP stands for the electrostatic potentials method. Shell P is derived from the ESP method. It stands for charge from electrostatic potential method. The next distribution analysis is the shell PG, is the charge from electrostatic potentials using a bit-based method. The next ESP is the restant electrostatic potential method, and the last sample is the MK, stands for merge command method.